So for the last few weeks, we've been studying a certain type of deductive argument, namely the categorical syllogism. At this point, hopefully it's familiar enough to you to know that a categorical syllogism is any type of syllogism that involves categorical propositions, that is, propositions that are about the classes of things, propositions that use quantifiers like all, no, some, or some not. But of course, these aren't the only type of arguments that are around. In fact, you might have been thinking you don't really see these arguments that often in natural language. The truth is you do, you just have to know what you're looking for. But even apart from that, there are a host of different kinds of deductive arguments, ones that are probably actually maybe a little more familiar to you. And in order to have a full understanding of logic, we need to study these as well. Now I want to begin by just giving you a few examples of the types of arguments, deductive arguments I should add, that you might see in everyday life. Here's an example or two of a common form of deductive argument. Either John cheated or it's the world's greatest coincidence that his answers are just like Becky's, and I doubt that such a coincidence occurred. In all likelihood, he cheated. Notice here this is a very common way of reasoning. It's basically saying A or B, not B, therefore A. It's an either or kind of argument. But of course this is supposed to be a deductive argument because given that the premises are true, the conclusion is supposed to follow with certainty. Here's another example. If you study hard, then you're more likely to do well in the exam. Sarah has studied hard, so she's more likely to do well in the exam. Notice this is a different kind of deductive argument, and notice that neither of these are categorical syllogisms because we're not talking about classes of things in these particular arguments. This second argument is a hypothetical sort of argument. It's a if A then B kind of argument, if this then that type of argument. This is a very common way we reason. Here's another one. If you study hard, then you're more likely to learn the information. And if you learn the information, then you're more likely to do well in the exam. So if you study hard, then you're more likely to do well in the exam. Notice this is also a typical argument. This one's a little different though than number two. And this one, notice that the conclusion itself is purely hypothetical. So if you study hard. So the conclusion is this kind of tentative if type of conclusion. Whereas this right here, the conclusion in number two, is not an if conclusion. It doesn't say so if then. It just says so therefore. Or actually that's redundant. It just says therefore. And the reason has to do with the premises. Notice this premise here is the second premise is not an if-then premise, whereas here the second premise is if-then. So in this example, I'm getting a little ahead of some information I'm going to give later on. This is what we call a pure hypothetical syllogism. It's purely hypothetical because the first premise is if A then B, the second premise is if B then C, and then the conclusion is going to be so therefore if A then C. Everything is hypothetical. It's turtles all the way down. Here's one final example. If abortion is always wrong, then it is impermissible for a woman to have an abortion to save her life. However, it is certainly permissible for a woman to have an abortion to save her life, so abortion cannot always be wrong. This is another example of a type of hypothetical if-then argument. The only difference in this one and let's say the second one is that here we're actually negating we're negating the second premise. And by doing that, we can then also negate our initial premise, so to speak. So here we're doing something a little bit different, but this is a very common way of reasoning. All of these are ordinary ways of reasoning, and we're going to be studying them as we move forward. Now, we're going to be looking at a type of logic that's different from what we've been studying so far. As I said a moment ago, we've been studying categorical logic for the last few weeks. But now we're going to move on to start studying what we call propositional logic. And I had talked about this a long time ago, so some of what we're going to cover today may be a little bit familiar to you, and hopefully it is. There's a certain method to my madness. I like to introduce things, let it sit for a while, and come back sometimes so that it's not entirely new the first time you're hearing it. But with categorical logic, you're basically studying how members of a class are related to members of another class. Whereas in propositional logic, you're not looking at class relationships. rather you are looking at relationships amongst propositions themselves. So if you look up here at this argument, all mammals are warm-blooded, all whales are mammals, therefore all whales are warm-blooded. Notice that the terms in each of the propositions, or each of the categorical propositions, is a class. Mammal is a class. Warm-blooded is a class. But if you go down here, if you look at this, if John goes to the store, then he will buy apples. John goes to the store, that's not a class. John going to the store is not a class of things. He will buy apples. That's not a class of things. These are actually their own propositions. John goes to the store, that is a proposition. John is going to the store, that is a proposition. He will buy apples, that is a proposition. We can do a quick side-by-side comparison here so that you can see what I'm talking about, and because it might be a little hard to comprehend when I'm just speaking this abstractly. But the terms within a categorical proposition are different than the terms within what we call compound propositions. Compound propositions are actually made up of smaller propositions. So if you notice here, whales is not a proposition, mammals is not, these are just classes of things. But over here, we actually have three propositions that we're expressing when we say if John goes to the store, he will be happy. First, there is John goes to the store, that is a proposition. He will buy apples, that is a second proposition. And then it's this entire thing, if John goes to the store, then he will buy apples. That is a third proposition. And when we go back, let's go back a slide here. What we're doing is we're looking at the relationship between proposition 1 is true, proposition 2 is true, therefore this proposition here must be true. So this is what we're going to be studying as we move forward. Propositional logic, that is logic that relates to, or logic that governs the relationship between propositions. We're looking at propositions like, right here we have this entire hypothetical proposition. Now let me go back a slide. This right here we have this entire hypothetical proposition down here at number 1. So if 1 is true and if 2 is true, must this conclusion also be true? There's a certain logic that's we're going to study as we look at this. Now, some of what I'm about to tell you is a reminder, but this is going to be important as we move forward. But as I just said, we're going to be studying what we call compound propositions. And compound propositions are propositions that are made up of other propositions using what we call connectives. And a connective is just basically any word or phrase that joins two propositions together. So, for instance, in English class, you might call these conjunctions. Some are conjunctions, but some aren't necessarily. But you have something like and. And joins two propositions together. I mean, and does other things, because I might say, apples, potatoes, and gophers. I'm not joining propositions together in that case. I'm just, listing items. But and is a connective when it's used to join two propositions together, or can join a couple of propositions together. If then, we've seen this already, or if and only if. Or you might say, although you gave me $5, you're still a jerk face, right? Although in that case is joining two propositions. You gave me $5 as one, you are a jerk face. None of you are. I don't know, my mind goes to negative places when I have to come up with examples on the fly. But although is a connective, but, I was going to give you an A, but you didn't turn in your final exam. That is a connective, is joining two propositions together. And we can see down here a couple of examples. I ran to the theater and I saw a movie. That's a connective. If John gives Sarah $100, then she will be happy. LeBron will win the MVP, or Steph Curry will win the MVP. See, it's joining two propositions. LeBron will win, or Steph Curry. The Cavs will win the NBA championship if and only if LeBron plays well. Well, this is over now. At this point, LeBron he's going to be a Laker. Praise the Lord, because I'm a Lakers fan. Anyway, these are compound propositions. And you can see here that they're made up of what we call component propositions. Now, I should say here that a component proposition is not necessarily one that doesn't have a connective. You notice in these down here, I ran to the theater, there's no connective. I don't have a slide for this, but this is something I said a long time ago, and we're going to actually revisit this in a couple of lessons. But when you have a proposition that has no connective in it, like I ran to the theater, or actually all the examples I have listed here in brackets, these are what we call atomic propositions. An atomic proposition lacks any kind of connective. But we can have component propositions that are a part of larger, that are themselves compound propositions, but they make up larger compound propositions. That was kind of confusing. Suppose I said something like this. I said, if John gives Sarah $100 and he smiles at her, then she will be happy. Notice then I would have a very large compound proposition. The whole thing I just said, if John gives Sarah $100 and he smiles at her, then she will be happy. But notice that that's made up of another compound proposition. John gives Sarah $100 and he smiles at her. That would be itself a compound proposition. So you can have compound propositions that make up larger compound propositions. That often is the case. Ultimately, what we're going to do is we're going to break things down all the way to the atomic propositions and study the logic of those. But I do want to kind of say at the outset that compound propositions can make up or be made up of other compound propositions. Hopefully this will make a little bit more sense as we move along what I'm saying here, but right now what I want you to take away are two important things. One, we're moving beyond studying categorical propositions, and we're now talking about compound propositions. Compound propositions and the logic of compound propositions and the logic of the component propositions. Compound propositions are made up of smaller propositions, which sometimes are atomic propositions, and sometimes are actually other compound propositions. So we're going to be looking at this, and as we study this, it's going to be important that we learn about what is called the logical form of a compound proposition. Now, compound propositions have logical form, as do arguments that are constructed out of compound propositions. They have what is called a logical form as well. And the logical form is basically the structure of a proposition or an argument once it's been stripped of all of its content. So you look at a statement like this: I ran to the theater and I saw a movie. There's a certain content to this. You're going to the theater. It's explaining this. You saw a movie. But there's also just a logical structure that this has, and the logical structure is the structure of, you might say, the proposition or the sentence that is devoid of the particular content of it. And the logical structure of this, the way we figure this out, is we identify the component propositions. In this case, the first component proposition is I ran to the theater. The second component proposition is I saw a movie. We identify those, and we identify the connective that's joining them. And then what we do is we set up a way to symbolize or represent these different component propositions. And we often use letters. Just like when we're studying categorical logic, we use S to represent the subject and P to represent the predicate. That was a way of symbolizing, using a method or a system of symbols to represent classes. Well, now we're going to be using symbols to represent propositions. Man, I keep having trouble saying propositions today. But we're going to be using a symbol to represent this first proposition here, this component proposition, and then a symbol to represent this. And we could use whatever we want. We could use A, we could just say, hey, we're going to let the letter A represent this, and we're going to let the letter B represent this. For whatever reason, I have no idea what that reason is. And logic, we often use letters P and Q. I think it's just because those are less likely to be confused with words. If you use the letter, like a lowercase a, for instance, we sometimes use A, like if I say a cell phone is on the desk. If you're using the word A as an article like that, and then you're also saying A, and then you have you symbolize something using the letter A, it might get confusing whether or not A is serving as an indefinite article or it's serving as a symbol for your proposition or your argument. So we use P and Q because I think maybe it's just because they don't get confused with anything else. But the way we would symbolize this right here is just as follows. Here's the logical form, P and Q. And notice that, like I said, this is devoid of any kind of content. The letter P just represents this proposition here. The letter Q represents this proposition here. And any statement that follows, that has this form right here, would have the same logical form. So if I said I ate bananas and I ate apples, notice that has the exact same form as P and Q. The same logical form. And that's actually what we study in logic. We study structural form. We're not studying. Validity is the validity of the form of an argument. It's not of the content of the argument. That's not what we're studying. We're studying the actual structure or form of the argument. So this one is a pretty straightforward one, I hope. It's just, like I said, don't get tripped up over, like, why do you, for the longest time I was like, why in the hell are we using a P and a Q? It's arbitrary. I could have used a squiggly line here and a squiggly line here, or I could use a circle for this and a square for that. This P is just a fill-in or a way to represent this proposition, and this Q is just a way to represent this proposition. And what I'm expressing down here when I say the logical form is just the structure of how these two propositions are related together, P and Q. Let's do another example. If John gives Sarah $100, then she'll be happy. What do you think the logical structure of this is? Well, first we have to identify the component propositions. And notice here I put the bracket around John gives Sarah $100. Then I put a bracket around she'll be happy. And we have if, then. And the logical form of this is going to be if P, then Q. I know, it's amazing, isn't it? It's amazing how this works. All right, well, let's do another one. LeBron will win the MVP or Steph Curry will win the MVP. Well, what's the logical form of this? Well, we're figuring out the structure that's been devoid of the content. We figure out the component propositions, and then we come up with a way to symbolize each of those. And this is just simply P or Q. Pretty straightforward. Here's another one. The Cavs will win the NBA championship if and only if LeBron plays well. Here again, we see the component propositions. We see our connective, if and only if. And here is the logical form, P, if and only if Q. One final one, and I didn't have a sentence representing this earlier, but look at this. John is not coming to the store. Now, you might think of this as being like an atomic proposition, one that's lacking a connective. But in logic, we understand the word not to function as a connective. And if we're breaking this down into its most basic atomic proposition, the atomic proposition here would actually be John is coming to the store. And the way we represent this when we're representing a logical form is just to say not P, where P represents John is coming to the store. So the logical form of this is not P. And it'll become evident why we represent this later on, why we don't just let John is coming to the store be, just symbolized with just say P, but rather we break it down to not P. It'll become evident why we do that later on. But I'm trying to give you guys kind of a brief understanding of logical form here because, as I said, when we study validity of these deductive arguments we're going to be looking at, we're studying logical form. So we have to first identify a logical form of propositions so that we can identify a logical form of an entire argument. Now, with that in mind, let's try to figure out the logical form of a few different arguments and see how this works. So take this is an oldie but a goodie. If you get an A, then you will pass this course. I don't know if the tense here shouldn't matter, but you get an A or you will get an A, therefore you will pass this course. What is the logical form of this argument? Well, the first thing we have to do is go through and figure out the logical form of each proposition. So let's look at that. And if you look at it, you'll notice that there's going to be some similarities here in what's being said. There's some propositions, some component propositions are getting repeated here. So let's begin with this first proposition up here. Number one, if you get an A, then you will pass this course. Notice what the component propositions of this are. The first is you get an A, and then as another component proposition here, you will pass this course. And let's just say we let P represent you get an A, and notice that P appears down here again. And then let's say we let Q represent you will pass this course. Notice that Q occurs again, just like it did down here. So, like I said, we could have let any letter we wanted represent this first proposition here, and we could have let any letter we wanted represent here. But once we settle on what we're going to use, if I'm going to use P to represent you get an A, then anywhere this proposition is repeated, I have to use that same letter again here. And anywhere this proposition right here, you will pass this course, is repeated, once I settle on the letter to represent it, I have to repeat it down here. And look at this right here, and hopefully you can see that the logical form of this argument is simply if P then Q, P therefore Q. That is the logical structure of this argument. And this is one we're going to study in some detail. I'm going to talk about this more extensively in the next lecture. But this right here, any argument that has this form, no matter what you say, no matter what you substitute in place of P here, as long as you substitute it in place of P here, and no matter what you substitute in place of Q here, as long as you put it in Q here, the argument will always be valid. This is a timelessly, necessarily valid logical form. Remember, validity does not relate to the substance or the content of what you were saying, but just the structure of what you're saying. So you could say something utterly asinine, like if Britney Spears is the world's greatest dancer, then God exists. And then I can come down here and say Britney Spears is the world's greatest dancer, therefore God exists. And that is a logically valid argument. Some of you are scratching your head and like, that is utterly stupid, because we all know Beyonce is the world's greatest dancer. No, but it's a stupid argument because the hypothetical, proposition 1 is just simply false, and proposition 2 is probably actually false. But that's not what determines validity. Remember, validity is if the propositions are true, then the conclusion must be true. And anything that has this logical form will always be valid. So that's why we study logical form, because once we can identify the form of an argument, then we can say, oh yeah, it is valid. Or we say, oh, look at that form is invalid. And this is important because sometimes, we studied the method of counterexamples a long time ago where we tried to develop a counterexample. That is, imagine a scenario in which the premises are true and the conclusion is false. But sometimes you rack your brain and you can't come up with anything. But you can look at the form of the argument and say, well, I can't think of why, a counterexample, but I can look at the structure of this and tell that it's invalid. So that's why studying formal structure is so important, because even in those cases where your imagination fails you and you can't come up with a counterexample, you can always look to the structure of the argument and say, well, just look at the structure and you can tell it's invalid. Let's do another example just so you can get some practice. If you get an A, then you will pass this course. You will not pass this course, therefore you will not get an A. And let's try to figure out what the structure of this, or the logical form of this argument is. And we'll go ahead and we'll identify our component propositions, and you can see there's some repetition going on here. But let's say we let P represent you get an A, and we'll let Q represent you will pass this course. And then we come down to number 2 here, and you might think that we put a Q here, but we don't, because even though I have both of these in purple, both of these right here, they look very similar. There's actually a very important difference between what they're saying. Notice this word not appears right here, and this goes back to what I was saying a second ago, really important lesson. But this proposition says you will pass this course. This proposition says you will not pass this course. And these do not mean the same thing quite clearly. So the way that we represent this, you might think, well, just use a different letter like S to represent you will not pass the course. But no, that's going to throw everything out of whack. The way we represent this statement right here is not Q. All right? And then the same thing is going to come down here. Notice this says you get an A, you will not get an A. And we represent this by, notice the word not appears there, not P, right? Because this is negating this proposition here. And so the way that we symbolize this, or the symbolic form, or the logical form of this, I should say, is as follows. If P, then Q, not Q, therefore not P. And this is a really hard one for a lot of times for students to see, but this is actually a valid logical form. And anything that follows this is a valid syllogism. Actually, the argument I had listed earlier, if abortion is always wrong, then it is not permissible for a woman to save her life, or the woman can't have an abortion to save her life, but she can have an abortion to save her life, therefore it is not always wrong. That is actually this logical form right here. It's of the form if P, then Q, not Q, therefore not P. And this is a valid way of reasoning. We do this all the time. We use this kind of reasoning. We'll say, well, if what you're saying is true, then this other thing follows, but that is false. So what you're saying must be not true. That's a way that we reason all the time. It's a very common form of reasoning. So I was giving you these as examples, not so that we study these particular forms right now, but just to be able to identify a logical form. Now there's one I do want to focus on a little bit today, and this goes back to an argument I had listed earlier. And we're going to study this one a little bit today and come back to those hypothetical ones next class. But let's read through this argument. Either John cheated, or it's the world's greatest coincidence that his answers are just like Becky's. And I doubt that such a coincidence occurred, so in all likelihood, he cheated. Well, we want to figure out the logical form of this argument, and first thing I like to do is just go ahead and get everything into premise-conclusion form. So this goes back to earlier lessons about distilling arguments. And here's the argument in premise-conclusion form. Now, what is the logical form of this? Well, we need to figure out what the component propositions are, and then we need to determine what the connectives are, and that'll enable us to know what the logical form is. And here we can see the component propositions. First, we have John cheated. That is actually a proposition. That's an entire sentence. John cheated. It would work as an entire sentence by itself. Here's another one. It's the world's greatest coincidence that his answers are like Becky's. Here's another proposition. I doubt that such a coincidence occurred, and he cheated. Now, let's say we let P represent John cheated, and Q represent it's the world's greatest coincidence that his answers are like Becky's. So Q is representing that. Well, the first statement here, you can already see, is going to be basically P or Q. Now, coming down here, we see John cheated. Well, boom, it's exact wording right here. That's pretty easy. We use the P to represent John cheated. We'll use a P down here to represent he cheated. Those propositions are identical. But what do we do about this one? It's the world's greatest coincidence that his answers are like Becky's, and then right here you're saying, I doubt that such a coincidence occurred. But those aren't saying the same thing, or are they? I think that what's going on here is this statement right here is just a kind of colloquial way to say that this is false, that Q is false. That's all you're saying. You're just putting it in a kind of natural way of saying it. I mean, you wouldn't normally say it's the world's greatest coincidence and his answers are like Becky's, and then follow that with saying, but it is not the world's greatest coincidence. So you'd say it conversationally in a different way. So I think that two is just, we can just say it's just saying not Q. I think that's all that's really being said here. So when we look at the logical form, here's this argument. P or Q, not Q, therefore P. And this right here is what we call a disjunctive syllogism. This is a second kind of syllogism that we're going to study in this class. Remember, we've studied categorical syllogisms. That's one. This is another kind, disjunctive syllogism. And what is a disjunctive syllogism? Well, here's a formal definition. It's a syllogism which consists of a disjunctive proposition. And you might be saying, what in the hell is a disjunctive proposition? Glad you asked. It's a proposition that is basically P or Q. Any proposition in which a person is saying, A or B, J or K, P or Q, any proposition that uses the connective or the word or is a disjunctive proposition. That's just what we call it. And the parts of the disjunctive proposition, the P and the Q, the two terms we call disjuncts. In a categorical proposition, we call, one of the terms the subject, the other one the predicate. And this one, if you have a statement like P or Q, you'd say, well, this disjunct, P is one disjunct and Q is another disjunct. So that's what a disjunctive syllogism is. Pretty simple, right? Any kind of either or statement, A or B, that's a disjunction. I know it's a new term. It's kind of scary sometimes. It just means or. That's all it means, or. And all you need to know is that disjunction is or, and we use it to refer to or, and the word disjunct refers to the parts of a disjunctive proposition, or I should say the terms of the disjunctive proposition, the P or the Q. It refers to one of those two. Now, I want to talk a little bit about validity for disjunctive syllogisms because it's not as easy as you might think. Now, we just saw this argument right here. John cheated, or it's the world's greatest coincidence that his answers are like Becky. And we saw that the form of this argument was P or Q, not Q, therefore P. And this is a valid syllogism. Anything that follows this form is always going to be valid. P or Q, not Q, therefore P. Anything that follows this will always be valid. No matter how silly what you put in place of P is, or how silly what you put in place of Q is, it will always be valid. Now, let's look at this argument. John cheated, or it's the world's greatest coincidence that his answers are just like Becky's. John did not cheat, therefore it's the world's greatest coincidence that his answers are like Becky's. I want you to pause it here and see if you can't figure out what the form, the logical form of this argument is. You might be thinking it's the same as the previous one. It's not. It's a little different. It's similar. Up to you. Well, the first premise is the same, but 2 and 3 are different. So figure out how they're different. Pause it and then come back. All right. Well, hopefully that wasn't too difficult for you. But the form of this is, notice you're saying John cheated, which is P, and then or it's the world's greatest coincidence, that's Q. John did not cheat. No, so you're saying P or Q, not P, therefore Q. That is the form of this syllogism. And notice here that this form is similar to this one, only in the first one we denied the second disjunct, whereas in this one we're denying the first disjunct. Now, is this a valid syllogism? I don't know, I wish I could have you here and ask your opinion, but I'll just go ahead and save you the suspense. Yes, this is a valid syllogism. Anything that follows this will always be valid. Always. Anything that has this form will always be valid. Well, let's look at one more example. John cheated, or it's the world's greatest coincidence that his answers are just like Becky's. John cheated, therefore it is not the world's greatest coincidence that his answers are just like Becky's. Now, I want you to pause it and see if you can't figure out the logical form of this. Again, this one's very similar to the others. The first proposition is the same, P or Q. But notice here, P is just being repeated. So this is P or Q. P, therefore, notice the not here, not Q. That is how this one goes. And the question here is, P or Q, P, therefore not Q. Is this a valid syllogism? And here is the tricky one. And the answer is no. This is not valid. This is invalid. And some of you are thinking, what the F? Why is this invalid? And this is actually something that's a little bit complicated, but it's important to explain. The reason this is an invalid form is because P or Q, P, therefore not Q, doesn't always work. Example 1 and example 2, these will always work. And an argument has a valid form only if it's always valid. But this right here, number 3, does not always work. And the reason it doesn't always work is because the word or is actually ambiguous. The word or has more than one meaning. And some of you are thinking, oh my God, this is getting so annoying right now. But I want you to look at this sentence right here. John will win the race or he will lose. Now there's 2 component propositions here. John will win the race, he will lose. And when you say something like this, what you mean is either one of these will happen and both can't happen, right? It's one or the other will happen. He can't both win and lose. But look at this proposition. I can play banjo, guitar, or mandolin. Which one of these can you play? Well, this is actually unclear. Because what you could be saying here is you can play banjo, but you can't play guitar or mandolin. You could be saying I can play, guitar, but not banjo or mandolin. You could be saying you can only play mandolin. You could also be saying you can play all 3, right? I can play, what this sentence here could possibly mean is I can play banjo, I can play guitar, and I can play mandolin. And this is important because the word or in natural language has both an exclusive meaning and what we might say an inclusive meaning. It can either be inclusive or exclusive. And when it functions exclusively, that means you're saying either one disjunct is true and the other one is false, but they both can't be true. And in the inclusive meaning of the word or, both disjuncts can possibly be true. And so we go back a slide here. The reason this won't function is because it could be, when you have the word or, in some instances, both disjuncts can possibly be true. So in the first proposition, there are going to be instances where both disjuncts are true. And so then the conclusion wouldn't be guaranteed because the conclusion is denying one of these. So this syllogism down here, where you affirm one of the disjuncts, it doesn't always work. And the reason it doesn't always work is because the word or is inclusive in natural language. And so we can't trust it as a valid syllogism. And so I just show you guys here, and maybe you can see the difference between valid forms and invalid forms. But the only times that the disjunctive syllogism is going to be valid is when you're denying one of the disjuncts. As long as you're denying one of the disjuncts, the disjunctive syllogism will work. However, if you have a case where you are affirming one of the disjuncts, where you're saying, yes, one of them is true, then that is a fallacy. And it's the fallacy of, creatively entitled, affirming the disjunct. These are actually only two examples here. There could be two more. You could say P or Q, P, therefore Q, or you could say P or Q, Q, therefore P. Those would be other invalid forms as well. But basically the commonality of all invalid disjunctive syllogisms is that you affirm one of the disjuncts. That just will not work in all instances. It will not always guarantee the conclusion. And so that's why it's invalid. Whereas over here, if you deny one of the disjuncts, the conclusion will be guaranteed as true. Now I should say here, if you were to deny this disjunct, and then you said, like, if you said P or Q, not P, therefore not Q, that wouldn't work. That would be an invalid form as well. But if this right here, the way I've worded it, if you deny one disjunct and then affirm the other, that is going to be a valid form. But anytime you affirm one of the disjuncts in order to conclude that the other one is not true or is true, it's not going to work. Anytime your second premise is affirming one of the disjuncts, it is always a fallacy of reasoning. So it's a little tricky at first because it does feel a bit unnatural from the way we often talk, because we'll often say, well, it's A or B, it's A, so it can't be B. But that's actually technically an invalid form of reasoning due to the fact that that form can't always be trusted. Now, in natural language, a lot of times the context of the conversation will actually imply more. You'll actually say a little bit more that maybe communicates that what you're meaning is, P or Q and not both. But on a formal level, this is an invalid way of reasoning. All right, well, here's your homework assignment for next class. And notice that I'm breaking the homework assignment between two chapters. You'll notice here that we're going all the way back to chapter 3.2. And the reason is because that's where the book first talked about identifying connectives and component propositions. And I just want you to do a couple of exercises in which you have to go through and identify component propositions, because that is going to be important as we move forward. But for these, I want you to identify the component propositions and the connective. For exercises 8.1, problems 1 through 10, I want you to determine the symbolic form of the argument and then identify if it's valid or invalid. All of these are disjunctive syllogisms, so they're all going to be P or Q. So it's either going to be something like P or Q, P, therefore not Q, or whatever. I just want you to write that out and then say if it's valid or invalid. If you have any questions, please feel free to email me.